In this video, we will be discussing phase diagrams. Now, what are phase diagrams? Well, basically, phase diagrams relate pressure and temperature of a compound and tell us when and where it's going to exist as a solid, liquid, or gas. Now, here's a very generic phase diagram. We have pressure on the y-axis and temperature on the x-axis. Well, let's think about this. If we keep our pressure the same, which in general we do, as we move from very low temperatures to higher temperatures, we go from a solid at low temperature, we cross this line here into liquid, we melt, and then finally as we increase the temperature, we're going to cross this line from liquid to gas, vaporization or boiling. Now, we don't necessarily have to keep our pressure the same. We can keep our temperature the same, and we can go from very very low pressures. And as we keep the temperature the same, and we go from low pressure, and we exert higher and higher pressure on it, we're going to take those gas molecules and compress them closer together, and eventually they're going to condense into a liquid. And if we get this up to high enough pressure, we will eventually cram that liquid into a solid. Now, what else is going on here? Well, we have a couple of other interesting points here. Literally, we have a triple point, and we have a critical point. Well, let's look at this triple point. If we manage to manipulate our pressure and our temperature just right, we lower our temperature, we also lower our pressure just a little, we can keep our compound right at the equilibrium between a solid and a liquid. It's a little bit of solid and a little bit of liquid. It's not melting or freezing, it's just staying right at the equilibrium between the two phases. Now eventually, as we lower that pressure enough and lower the temperature slightly, we're going to come to this point, the triple point. Well, rather than being on the equilibrium between solid and gas, or solid and liquid, or liquid and gas, the triple point is actually the equilibrium point between all three phases. Here's a really good example of what the triple point looks like for hexane. Here we have lowered the pressure using a vacuum to a point where, well, yeah, actually we can not only condense the gaseous hexane, but then we can freeze it. And if you manipulate it just right, you can keep those three phases right at equilibrium with each other. Now, what's this other point? The critical point. Well, the critical point has to do with supercritical fluids. You notice our equilibrium between gas and liquid stops at the critical point. Well, what this means is that at this beyond this temperature and beyond this pressure, the phase between liquid and gas is indeterminable. It doesn't exist. And this is where you get something called a supercritical fluid. Here we have carbon dioxide. Now, you don't normally think of liquid carbon dioxide, but if you exert enough pressure on carbon dioxide gas, you can actually get it to condense into a liquid. This has to be done at very high pressure. Normal atmospheric pressures, you do not get liquid CO2. It just doesn't exist. Now, in this example here on the left, we have subcritical carbon dioxide. We actually have the liquid form. And we have two little ballasts in there. They both have a lower density than liquid carbon dioxide at this point. However, as we increase the pressure and the temperature, we get to supercritical carbon dioxide. Notice that the liquid phase here no longer exists. And our two ballasts, the very low density one is floating, and our high density one, which is higher than the density of supercritical CO2, has dropped. Now we can lower the pressure again, and we can go back to subcritical, and these two ballasts will come back to the same level. So this is supercritical fluid. This is what you get when you have pressures and temperature beyond the critical point, where you lose the difference in the lose the difference in the liquid and gaseous phases. Now this is what your typical phase diagram may look like. You have your pressure, in this case atmospheres, on your y-axis, and temperature on the x-axis, in this case in Kelvin. Usually the line between solid and liquid leans a little bit to the right, and you can determine, say, at 1 atmosphere that the melting point is around about 60 or 70 Kelvin, and the boiling point at 1 atmosphere is about 225 Kelvin. If you wanted to go to 1.5 atmospheres, the boiling point would be about 260, and the melting point would be around 75. Now compare this to the phase diagram of water. Here, the equilibrium line between solid and liquid leans to the left. Well, what this means is that as you take solid water, say at 1 atmosphere, and you exert pressure on it, well, it actually moves into the liquid phase. And this is due to hydrogen bonding. As the solid, as water solidifies to a solid, it rearranges based on that hexagonal system because of its hydrogen bonding. As you increase the pressure, you disrupt those hydrogen bonds and you actually liquefy it, which is counter to what normally happens in most compounds. Most compounds, you increase the pressure, you actually solidify it. And of course, we have some much more complicated phase diagrams that we don't talk about in this class, but they do exist. Now, going back to the phase diagram from water, we can actually determine a lot of information from this. At standard atmospheric pressure, 101 kilopascals, or 1 atmosphere, the normal melting point, that's the melting point at atmospheric pressure, is 0 degrees Celsius. The normal boiling point is 100 degrees Celsius, as we can see that right here. The triple point is at 0.6 kilopascals and 0.01 degrees Celsius, and the critical point is at 22,089 kilopascals and 374 degrees Celsius. So this is the information that we can determine from a phase diagram. Now keep in mind, you may not always see the actual phase, solid, liquid, gaseous, but it should be obvious where they show up on a phase diagram.